Hello everyone, my name is Sebastian and I'm the founder of Pimax Studios and DC Spark. And in this video, I want to talk about two projects we work a lot with. One is called Mina and the other one is called Midnight. I think both of these are brilliant projects, which is why I work with them. But I think a lot of people that we talk to aren't really familiar with these projects. They probably heard the name multiple times, but aren't really sure why we're using them or what's so interesting about them. So in this video, I want to talk about both of them because they're both related projects but implemented in very different ways. That's to say, they're both ZK based projects. ZK stands for Zero Knowledge Cryptography, and I'm going to explain what that is in a second. But they're both ZK based blockchains that have this feature called recursive SNARK. And I'll also explain that later in this presentation. And they do this while also preserving privacy, which I'll also talk more about what exactly I mean by quote unquote privacy later on in this presentation. But the key thing is that there's these two different layer one blockchains that both try and not be full layer ones on their own, but focus on composability with other ecosystems, and to achieve this kind of composability and these integrations, they leverage ZK and they make this ZK efficient uh, by leveraging these two techniques. So similar projects, but they're implemented very differently. And we'll see in this presentation how they're implemented differently and how that actually affects the developer experience and what you can do with these platforms. So now that we have some background on what we're going to talk about, now let's get into it. And first, I want to describe a bit zero knowledge cryptography. So it'll be a very, very quick introduction. And within this, I'm also going to explain recursive SNARKs. So some of you may already be familiar with what it is, but if you don't, we're going to explain this with a game called Where's Waldo. So if you're familiar with the game Where's Waldo, you know that basically you have a map with buildings and people and a whole bunch of different things going on. So maybe there's like a dragon or a bird or something. And within all that noise, there's a hidden character called Waldo, and your goal is to find him, right? And so what we're trying to talk about is ZK. And when you hear the term ZK, usually there's two concepts that are used, and you don't always get both. So one of them is compression, and the other one is privacy. Now, when you hear projects saying, "Oh, we're a ZK-based project," they're talking about the underlying math, and they usually use ZK to get one of these two things, and sometimes both. So we're going to explain both of these properties with this Where's Waldo game. So how do we do that? Well, imagine you as a person know where Waldo is. You've looked through the map, you've looked through all the objects, and you found them. You know where it is. And you go to your friend and say, "I found Waldo." Your friend says, "Okay, well, prove it to me. How do you know that Waldo's there?" Well, you could of course just like point, like, "Oh, well, he's right here," but this would reveal to your friend where Waldo actually is. So you're revealing the information. Maybe you don't want to reveal the information. Your friend hasn't solved the puzzle yet, or hasn't found him yet, and you don't want to spoil it. You don't want to ruin the experience for your friend. So you want to prove to your friend you found Waldo without showing your friend exactly where Waldo is. So how do we achieve this? Well, imagine we had a large sheet of paper and we covered the entire Where's Waldo page with this sheet of paper. I know this paper is not transparent. So your friend can no longer see the board, everything's gone, they just see this giant sheet of paper. Note that the actual piece of paper could be anywhere, right? It could be down here, it could be over here, it could be in the corner. No, like the important thing is this giant purple sheet is large enough such that the underlying uh, page, the underlying Where's Waldo page behind it could be anywhere. Okay. And then you're gonna cut a hole in this piece of paper just big enough to reveal Waldo behind. So now your friend knows that you know where Waldo is because they can see Waldo. He's right there. But you only cut out this section. So the rest of the page this is still transparent. So your friend can't see where in the page Waldo is, because remember the page could be up here, the page could be down here, it could be down here. They don't know where the paper is. They don't know where Waldo is in the paper. They just know you found them because you were able to cut out a very specific hole exactly where Waldo is. So great. Now let's talk about privacy and compression, right? So of course now you get privacy, which is that your friend doesn't know where Waldo is. He just knows he's there. Um, but you also get compression, which is that your friend could say, of course, where is Waldo? Is a valid question to ask. But another valid question is there a Waldo? Right? Somebody could give you a piece of paper and not even be sure Waldo is on the page or not. But now you have a proof that Waldo really is on the page because you revealed him. So you're able to answer the fact that you know where Waldo is, but you can also answer the fact that is there a Waldo? Yes, I know there's a Waldo, and here it is. So know that this is kind of a concept of compression because you're able to convince somebody that Waldo exists on this page with a very small amount of information. You didn't have to reveal anything about the page other than just a very tiny hole where Waldo is. So just a very small amount of information, you're able to convince somebody of a statement. Now, this may seem kind of contrived. Why do we care about this? But this matters a lot in the context of blockchain, right? So you might have a blockchain, and you want to be able to have a layer 2, for example. Like there's a very common concept called a zk rollup, and you want to prove to the underlying blockchain that there is some block in this layer 2 that is valid according to a certain set of rules. So, for example, you say, okay, this is a layer 2 that's zk EVM. It's a layer 2 that uses the EVM. And here's a layer 2 block. Maybe like we're going to represent this layer 2 with blue. Okay, so here's a layer 2 block, some information. And I want to convince the layer 1, which is in purple, layer 1. I want to convince the layer 1 that this blue block is a valid layer 2 block, right? And we want to be able to convince the layer 1, which is a smart contract, that there's a valid layer 2 block in as few bytes as possible, right? Because the more bytes you have, the more data you need to upload to the blockchain, which hurts not only scalability, but also increases the transaction cost, right? This compression allows you to prove statements with a very little amount of information, and this is what essentially used to take these layer 2 blocks and very efficiently prove their correctness within layer 1. So a lot of times when you hear about ZK rollups, they're often not using privacy at all. The main reason they're using ZK is the compression. They want to be able to create very distinct, very small proofs that there is a valid layer 2 block with a specific hash, right? So they're just trying to prove a statement in a very distinct way. But some projects do care about privacy as well. And oftentimes, the reason we care about privacy is for use cases like real world assets, right? You'll often hear companies say, like, well, I want to use blockchain, but I can't have health records on chain. Like, that would be a, privacy regulation problem. This It's not acceptable that anybody can see anybody's health record at any time, right? So maybe you want to use the blockchain for some kind of coordination or some kind of system, but you don't want to reveal the health record. But you might still want to be able to prove statements about somebody's health record. You might want to be able to say, like, okay, here's a proof this person had a healthy checkup without revealing any specific information about what happened during their health checkup, right? So you might really care about being able to make statements about the data without revealing the underlying health of the user or the underlying medical procedures they've had done. So it's super useful for real world assets, also really useful for gaming, right? So you hear a lot of people talking about gaming with blockchain, so people can trade assets and people can have a more dynamic game world that evolves based off contributions of players and having games that live forever. So the game is not shut down, which is a very common problem in like mobile games where people pay a lot of money for digital assets inside the mobile game, then the game just shuts down and they lose everything, right? So with gaming, privacy is important because we want to have stuff like fog of war or not knowing what the opponent is doing, right? So you want some kind of privacy to make the game more exciting and more fun and more strategic. And of course, in gaming, we still care about compression, right? We still want something that's a large, complex experience like a game to have a very succinct proof on chain. Otherwise, the whole thing will not scale. So great, we've seen that compression and privacy is useful for real world assets. It's useful for gaming. Of course, it's useful for DeFi as well. If you want to have liquidity pools where you can't get sandwich attacked, so privacy is useful there as well. So a lot of cases where privacy is useful. A lot of cases where compression is useful. And so that's why ZK is useful in general. And so both Mina and Midnight enable this kind of privacy. So a lot of ZK rollups and kind of systems don't. But Mina and Midnight are somewhat unique in the sense that they also don't just do compression, but also support privacy as well. And we'll see a bit more about that concretely. But before we get too much into that, what is this recursive snark concept I mentioned earlier? Right, we mentioned it's not just ZK, it's not just traditional serial knowledge cryptography. It also has this concept of recursive snark. What is that? So to understand that, note that oftentimes we care about proving multiple statements, right? So maybe to extend our previous example, right? We had this Where's Waldo example. Maybe you don't have just one Where's Waldo book. You have 5 books. Maybe you want to prove, where Waldo is in every page of a book, right? It's not just one puzzle you're trying to solve, but a whole set of things, right? So how would you do that? Well, we could have like before. We have this giant sheet of paper, right? And behind it, we have multiple books, multiple Where's Waldo books. And we similarly cut out a hole exactly where Waldo is in all the books. So note that you don't actually know where the books are like before. So just like this. You're only revealing the position of Waldo. So with this, you've been able to convince your friends that you know where Waldo is not just in one puzzle, but actually in multiple places in multiple different books as well. So you're proving multiple statements. And if you think about it, if you were to align all these properly at the same spot, like you moved all the Waldos to the same spot, the amount of space required for this is actually very small. And usually these kinds of recursive snark systems are basically doing something similar to this conceptually, which is that they allow you to combine multiple proofs together into a single proof, and oftentimes, not always, but oftentimes they're constant size. So no matter how many statements you want to make, no matter how many Waldos you want to prove, the proof that you know where Waldo is always some constantly sized number of bytes. So great, now we have this concept of recursive snarks that allows us to take this really powerful concept of ZK and use it to prove multiple statements at once with very little overhead, right? Instead of having to have 10 different sheets of paper, we can just have one sheet of paper with just multiple holes, so the size of the paper does not necessarily grow. So we have this constant size way to generate proof that we know where Waldo is across multiple different stuff. So this is kind of like a high level explanation. Again, this is not trying to get too much into math, what I really want to convince you is that ZK exists, and there is a way to make these protocols work, right? So I'm not going into the math exactly how it works, but rather just trying to give you an intuition that this is possible. Because you probably know one of the hardest things about learning is oftentimes the mental blocker. You see a page describing a concept you don't know, and it's like, oh, I don't know, like, I forget it. I'm not even gonna read the page. Like, you just mentally block it out. And so the point of this kind of Where's Waldo example is to help you kind of not be as scared of this concept. You're like, okay, like I don't maybe know the math or how it's in detail, but I can conceptualize that. There is the kind of statement where you can do privacy and compression, and there's some kind of cases where you can combine statements together in an efficient way, and that helps you get over this mental block and get to the next level. So now that we know more about what Mina and Midnight are trying to do, right? We have these two cool projects that both do similar things. Now let's talk about their implementation, because they're implemented in very, very different ways, and they'll have big repercussions on what is easy to do with these systems, what's hard to do, what is the developer experience like, and so on. So with that, let us clear the board and start with Mina first. So I'm going to start with Mina, because I think it's a bit conceptually easier to understand. And understanding Mina will also help you understand why Midnight is designed the way it is and how it's trying to solve different issues with Mina. So Mina calls itself a succinct blockchain. So what does that actually mean? What is a succinct blockchain? So if you think about a typical blockchain, for example, Bitcoin, you have a whole very, very large history of blocks. And if somebody asks you what happened in block 1,000, it's very hard to prove this statement efficiently. You'll have to say, okay, well, let me run a Bitcoin node on my machine, start at block 0, download block 1, download block 2, download block 3, all the way until you get to 1,000, and okay, I've gotten to block 1,000, and here's the result. Now, there are some algorithms to try and get information out of Bitcoin in a way that is faster. So you can find some projects about this, like Flight Client, NepoPow, SPV. So there are some concepts to try and get information out of Bitcoin faster. But at the end of the day, to be able to generate these statements, somebody needs to hold the full blockchain. And so this is somewhat problematic, because it means that if you want to run a full node on your machine, you need a lot of space. So it takes a lot of storage. And Bitcoin is not that bad. The blockchain is not that big. But blockchains like Ethereum, which has a lot more state, you could be looking at hundreds of gigabytes or terabytes depending on how much information you're looking to store. And for blockchains that produce a lot of data, like the Solanas of the world, then this gets even worse. The system requirements to run a full node make it such that it's not really accessible from a consumer hardware perspective. You need to be able to go buy more expensive hardware specifically to be able to handle the amount of storage and data handled by Solana blockchain. So this is the downside of traditional blockchain architectures, that somewhat by design they require you to have the whole history of the blockchain to be able to prove many statements about it, and telling the full history of the blockchain is space inefficient. So the question is, can we do something about it? Well, let's go back and think about ZK. Can this technology help us solve this problem? So in the traditional blockchain, you have blocks. In between blocks, you have transitions. You say, like, okay, I started at block 0 and then went to block 1. And so there's some kind of transition in the blockchain state. What if we had a ZK proof that this transition is accurate? We say, okay, given that there's a block 0 and some new state block 1, here is a proof that block 1 really can be generated from block 0. Right, so note that this is kind of conceptually similar to our where Waldo problem. Remember, we're trying to figure out, is there Waldo on the page? Is there even such a Waldo that exists somewhere? And here, similarly, we're saying, is there such a transition to go from block 0 to block 1? We want to prove that, sure, there is some step transactions, some different things that could happen. That is a valid transition from block 0 to block 1. So with this key insight, we know it's possible to create a blockchain where the transitions between blocks are ZK proof. Okay? But why is this useful? Now, one of the key insights to making this useful is remembering the concept we talked earlier about recursive SNARKs, which is one of the more well-known techniques for combining proofs together. Remember, we said with recursive SNARKs, we can take two proofs and combine them together into a single proof. So what does that look like for our example down here? Well, let's color code this a bit. So we'll say block 0 is in green, and this last block, this most recent block, here is in yellow. So how do we know that block yellow is valid? Well, we have, a proof here, and another proof here, and another proof here, and so we can validate this chain of proofs to get all the way to this yellow box. So okay, we know there's a path from green to yellow, but it requires us to check multiple proofs. In this case, we have to check one ZK proof, two ZK proofs, and a third ZK proof to get to the final block. Recursive SNARKs allow us to combine proofs together. So we could have is block 0, and then our most recent block. Instead, our proof here is 1 plus 2 plus 3. It's a combination of the 3 different proofs that got us there. And this is really awesome because it means that to prove the entire history of the blockchain, we no longer have to download every single block and verify them ourselves. Rather, just with the genesis block, the initial block of the blockchain, the most current block, to know what the current state of the network is, and a single proof that shows that there is a path from the genesis block to the most current block, we can have knowledge that this is a valid copy of the blockchain. Now, I want to slightly caveat this for the people who are watching this who are like, oh, but blockchains, as you might know, might have different branches. So there could be multiple different blocks that are valid, and to find which of these blocks we really care about, you do need something like proof of stake or proof of work, some kind of Sybil resistance or weighting system to make sure that people go on the right path. And so you don't really have to think about this for the concept of this presentation. This is more for the pedantic type. This is with our ZK system, we get a proof that there is a yellow block that's a valid extension of the genesis block, but it does have to be combined with another technique, that it's the extension of the genesis block that we care about. Okay, so now we know we have this really cool way to create a succinct blockchain. The reason I bring all this up is because this is exactly how Mina works. So Mina is a succinct blockchain that uses this ability to combine ZK proofs together to shrink the blockchain down into a very succinct representation. But let's think about what Mina does a bit more low level, so we can really think about how this will compare to Midnight and see the implication of its implementation. So you've probably heard this concept of smart contract. And smart contracts are usually something like, contract ERC20, ERC20, and inside it they have like a transfer function. They have maybe a receive function. They have an allow function. So you can find online the entire interface for ERC20. But the key thing is that contracts for smart contracts um, usually have some kind of name and a bunch of functions that they support, and then usually they have some kind of state. So usually there'll be some kind of mapping of address to value, where it says like Vitalik owns these many tokens, and somebody else owns this many tokens, right? And you own this many tokens. So there's kind of mapping between user address and how much of that token they own, and then some functions to operate on this data. So if you think about it, in a sense, these smart contracts are mostly just mathematical functions. Okay, so we can think of a function as just sometimes function like foo. If you don't know, foo is like a commonly used placeholder name in programming language circle. So a function called foo, and inside it, it does some stuff. Maybe it transfers some money, it does whatever. And inside it, we call some other function called bar. If you don't know, bar is like another one that's programming placeholder names. So there's our function foo. It does something, it calls a function bar. So the key thing is that functions in programming languages can call other functions, right? So you have a function definition up here, and this function calls another function. So how does this relate to ZK? How do we ZKify these smart contracts? Well, what we really want is an algorithm that takes in a function, a mathematical function as input, and turns it into a ZK circuit. A ZK circuit is what is generally used to create ZK proof. Circuit kind of hints to the fact that it's kind of like a electrical engineering, like an actual circuit board. We have wires and kind of stuff. So it's the same kind of concept, which is like you have a bunch of stuff happening and it crosses a path and then it generates the statement at the end. So it's kind of borrowing from this electrical engineering term. So these things that can generate proofs, we usually call them ZK circuits. And so what we really want is some way to take a function, a mathematical function, and from it create something that can generate ZK proof. Okay, and there's many known ways to do this, oftentimes called arithmetization, but you can find more different literature on this if you're interested. But the key thing is that note that we want to turn foo, our function foo, into ZK circuit, but inside it there's bar, which is a separate function, right? Somewhere else there's definition, function, bar, this stuff. So we have to take into account composability, right? How do we ZKify, turn into ZK circuit, ZKify, a function that might itself depend on other functions? So to solve this, oftentimes what is done is instead of generating one giant proof of everything, which is possible, it is one approach, we could do is generate a proof of bar and embed that proof within a proof of foo. So if you think about it a bit more visually, you have a proof of bar, and you're embedding this inside the larger proof of foo. So maybe to color code this a bit, this is our bar over here in purple. And we're saying we're embedding this proof of bar within a larger proof of food. This bar is inside food. So if you think about it, this proof composition is kind of like recursive SNARK, right? You're able to combine proofs together. And so this is the key insight that enables Mina to work, which is, okay, we can have proofs of functions, and we can compose these functions because we support proof composition, right? We had a way to combine proofs together. Therefore, we can also combine functions together. So if we go back to thinking about this, back to the block level, a transaction is a function that might call other functions. And so you have a bunch of stuff, and then this gives you a transaction. Well, what is a block? Well, block is just a set of transactions, which might be doing other things. And so remember, we were composing proofs a function. So transaction is just a function, which itself is multiple things. A block is also just proof composition. You're taking a bunch of proofs of transaction and combining it together into a single proof of block. Then what happens if you have multiple blocks? Well, blocks are just transactions. Transactions are just functions. And functions are just combinations of multiple proofs. Therefore, your blockchain is also just a combination of proofs. So hopefully this gives you a cool insight into like the mathematical beauty of Mina, which is that, okay, if we can represent mathematical functions as decay circuits, and we have the ability to combine proofs, then we can generate proofs of functions. And by generating proofs of functions, we can generate proofs of transactions. And by combining proofs of transactions, we can create proofs of blocks. And by combining proofs of blocks, we can create a proof of a blockchain. And that's the real beauty of this, recursive SNARK and distinct blockchain. And this enables you to do stuff like very efficient layer 2s, very efficient bridging, very, very efficient privacy for things like real-world assets and gaming and DeFi and so on. So that's why a lot of people have been excited about Mina historically, and why it's one of the more well-known CK projects, because it's a really interesting idea that seems to solve a lot of the problems that the industry has had. But what are some of the downsides of this approach by Mina? Well, know that smart contracts, as I mentioned, they're typically two things, right? You have the data and the function. So you see in our example, we talked about how we can map functions to proof. But what about data? Right? If we compress our entire blockchain into a very distinct small representation, where does the data get stored? How do you know the state of a smart contract? And this is one of the issues that Mina struggles with, state management. So smart contracts in Mina have very limited state. So you need to find a contract in Mina. You can have some state. So it allows you to have some variables. But they have a limited size and a limited amount of variables that you're allowed to declare. And when you have state in Mina, the state of the contract will be propagated to the nodes that were around when the state was calculated. But nodes that weren't around will have to fetch the state from a different node, right? So remember, think about this more actively. Like if you were to download the Mina blockchain today, You just get this. So to get the actual concrete state of the smart contracts, you're gonna have to fetch this state from other nodes. You're gonna have to ask other people that are running full nodes, like, hey, I know the contract, or sorry, I know the blockchain state. Generally speaking, give me the state that corresponds to this blockchain. So know that you can't lie. You don't trust these people. You don't have to trust these people. I have to think why is because when you have the full blockchain state, right up here, you have the full blockchain state, you know the final result of everything. Like, you know, oftentimes called like the hash or the Merkle tree. You might have heard some of these concepts. You know the final state you're looking for. You know, okay, this is the current state of the blockchain. Is some set of numbers, and you're just asking nodes to please give you the what's sometimes called the pre-image, the information that maps to the hash function. So maybe to say this in a more intuitive way, imagine you knew the address of where you want to go, but you don't know how to get there. If somebody comes up to you and gives you a map with the path for how to get to where you're going, you can easily check if they're giving you the right path or not. Because does the end at the right address? Does it start at the right place? Right? You know where you started. You know where you're ending. You just need somebody to fill in the gaps, and when they give you this like the path you need to go to, you can easily check like, oh yeah, this matches what I was thinking of getting. So you don't have to trust the people giving you the state, but you do need to get the state from somebody. Right. So this is the downside, and this is why a lot of Mina dApps that require a lot of data to operate struggle to get to Mina a lot. Now, in a separate video, I'll talk about how Mina is addressing this, and they have a system called Project Untitled, which is a new project by the company O1 Labs, which is the company that created the Mina blockchain, or one of the companies that created the Mina blockchain. So they do have a project that's meant to solve this, but it requires a bunch of extra explanation, and it is a very interesting project. I think it's a well engineered, but I think this video is probably going to be long enough as it is, so we're going to get into that in a future video. I know that they do have some plans for this, but it's a bit involved. So we talked about how, you know, representing state is a bit of a difficulty for Mina, but there's actually a related issue we need to talk about as well, which is concurrency. Right? How do we handle concurrent access to the same state? So what does this matter? Well, imagine you had a DEX. A DEX often has liquidity pools. So it has a liquidity pool. Inside it, there's token A and token B. And both these have a price. There's some kind of ratio between the tokens. Maybe for every token A you put in, you get back 2 token B. So there's some kind of ratio. Now, when somebody places an order on a DEX, they want to buy an asset. Usually there'll be a setting that's slippage. Right, this is the current price, but the price might change over time. So what is the maximum price difference you're willing to accept? Maybe if the price changes by 5%, you're still willing to go through with the trade. And you need this kind of slippage because blockchains are dynamic. The value is always going up and down, up and down, up and down. By the time you've signed your transactions, send your transactions to the network, the price might have changed a bit. So slippage helps with this. So this is kind of a concurrency issue because you have a blockchain state, but the state is shared between many, many different people. And so you need to somehow ensure that when you're interacting with these smart contracts, with these states, that the fact that other people interacted with the smart contract before you does not break your transaction, does not cause issues, right? So slippage is kind of a solution to this because it says, okay, other people might interact with the smart contract before I do. They might change the price a bit before I do. But by the time my transaction comes, by the time it's time to process my transaction, as long as the price is maybe 5% of where it originally was, I'm okay with it. Okay, so it's the solution to this concurrency issue. Concurrency in the ZK setting is a bit harder. Because remember, in the ZK setting, we have a proof. Okay? And the proofs are generated from a specific state. Right? For example, we say, like, given this is the Genesis block, then we can make this transition. Or given this is, block 3, this is block 4. Right? So usually ZK proofs work by saying, okay, assuming a current condition, here's the next potential step. But this is a bit hard in this concurrency setting because how do you say a statement about the current state of the deck if the next decks might change by the time you actually get to use it? So every ZK blockchain has to have a way to handle this kind of concurrency issue, which is how do you make the proofs be a bit malleable? So you can prove statements not about the current decks as it has to be right now, but rather say I want to do this as long as this state generally still holds. So the way that Mina does this is with the concept called reducers, which is that instead of swapping right away, instead of transacting with a deck right away, you want to queue up action. So you want to say, like, I want to trade. So instead of saying I am trading right now, you're saying I want to trade as long as, with some conditions. So instead of saying swap right now, you're saying I want to trade as long as these conditions are met. So people create these kinds of actions that they want to perform. And so you have your action, somebody else's action, somebody else's action, a bunch of people have actions. And then later on you reduce, which is a programming language terminology. But reduce means take everything that's accumulated so far, right? So we have a bunch of actions that have accumulated so far. We want to take all these actions and reduce them to a single result. So this is kind of like batching. You have to batch all these actions together into a single transition to update the state of the liquidity pool. And as you're reducing, you might say, okay, process this DEX, the swap request, it still has the right slippage. Maybe this one is no longer valid. The price has changed too much. Their as long as is no longer satisfied. Maybe this one's okay, and maybe this one is no longer satisfied. So this reduction allows you to take all these intent, these actions people want to do, and actually perform them, throwing away things that no longer need to be processed, and then generating you the final result. So this concept of reducers is super important to handle concurrency. So great. This kind of solves our problem with Mina, and this gives us, as an end result, a very succinct way to represent the blockchain. Do it in a way that still handles some state, and a way that we can still have concurrency. Okay? So now that we have an idea of Mina, we can see that it's pretty clever as an approach. It allows us to model everything as function, model everything as function composition, and with this we get this really nice system. The downside is that the data is a bit hard to handle. You have to think about, oh, I have limited state. How do I handle this limited state? You have to think about the fact that state comes from different nodes. How do I know there's different nodes that have that state? How do I deal with concurrency? How do I deal with the fact that people might want to update the different state at the same time? So there's a lot of um, issues with trying to build a large system with Mina when you're building an application that is very state dependent. That's a lot of state that can change in many different ways with a lot of concurrency. It can get really hard. So now that we have this concept of how Mina works, now let's talk about Midnight. Which, remember, Midnight is also a blockchain currently based on recursive SNARKs, and it also supports privacy and compression, and also is trying to connect to other chains. So it shares a lot of conceptual overlap, but they're trying to tackle this in a different way and think about things in terms of data. So, in one way to think about it, and this is conceptual way to think about it. Mina is kind of like function based, which is that we think of everything in terms of function, and everything is just function composition. You're just combining functions together, combining more functions together, combining more functions together. And so a lot of the mathematical beauty comes from the fact that you're building an entire system just by having this simple construct. ZK circuits are functions, and taking that as far as you can. In Midnight, it's kind of a similar thing. But instead, it's trying to model everything as variable update. Now again, this is a conceptual thing. These are both Turing-complete blockchains, which means like anything you can do in Mina, you can do in Midnight. Anything you can do in Midnight, you can do in Mina. But doesn't necessarily mean it's as easy to do it. And so, kind of conceptually, Mina tries to think about this more a variable update based approach. What does that actually mean in practice, though? I mean, so when you define a smart contract in Midnight, you have a bunch of states like before. So you might say like, okay, this is like mapping of who owns the tokens, and maybe this is like if it's a game, it's like how many lives each player still has remaining, and then maybe it's like how many points the players have. So you have a whole bunch of states inside your smart contract. And what people submit to the blockchain as transactions is updates to those states. And the proofs are used just to prove that there exists a way to update that state. Remember, in Mina, we're trying to prove transitions between blocks, which are just transactions or chains of functions. And maybe I should use what for this. So this is like the Mina case where you're just trying to model things as functions and combining functions together, and that's how the blocks are chained together. In Midnight, what you're trying to do is saying, okay, well, a transaction is just updating a certain set of variables. So you have a bunch of variable updates, and your blocks are kind of these variable updates. Conceptually speaking. And so instead of modeling things as a bunch of functions being composed together, your genesis block to the final block of the blockchain is just a bunch of variable updates that have happened over time that results in a final set of variables. So it's a bit of a different way of thinking about things. And part of the reason this is useful is because it gives you a nice way to think about modifying data locally. Let's say, imagine we have some kind of game. The game, as we saw earlier, has some kind of master contract that has, the lives and the points and all this kind of information that's global to the game. But each individual player has some state that's local to them. Right? So the player might know their position and how much gold they have and other information that's unique to each player that they don't want to reveal to anybody else. Right? Because we wanted privacy in these games. We want some secret information. And these players are, moving units around, spending gold. And at the end of the day, what they want to do is they want to increase their point. And so what you're basically doing is you're generating a proof that there exists some private state that I have. And if I use this private state in a specific way, it gives me 100 points. So you're proving an update to a variable based off some private history, which is represented by this set of data that you own. So this kind of model in Midnight is much easier to reason about if you're building an application that has a lot of data. Because unlike Mina, it's not trying to compress everything into just 2 blocks. It's not like, oh, there's a genesis block, and this is the final block, and here's your one state transition. It could be modeled that way, but it doesn't really try and do this. Rather, it tries to publicly have some variables that are stored in the typical kind of like Bitcoin-like fashion, which is a bunch of blocks where inside these blocks you have the public variables all listed. When you deploy a new smart contract, you add some new public variables to the blockchain. The transactions people are making are proofs of updating these public variables based on private state. So law is a more intuitive way to model this kind of concept of actors have different private information. For example, you might have private balances or private trades in DeFi protocol, or private healthcare information in real world asset case, or private game state in a game. You as the user have some private state, and you occasionally leak some information. You share some information about your private state through proof to update points. So people who are watching from the outside, for example, this person, they could, for example, see that you've gained 100 points. They don't know what you did to get 100 points. They can't see into your private state. But they know that you did something that had a valid proof to update your point, by 100. So this kind of concept in Midnight has a much easier way to have consensus on public state and easily share that public state with a bunch of different people, and we all agree on the public state. And we're all participating together in the same dApp, and instead of sharing private state at any point, we're instead just submitting proofs that we did something to get more points, we did something to get more lives, we did something to get an item, we did something to be able to trade an asset, right? And so it's a bit of a different way of thinking about things. Now, this does not mean that you magically solve the concurrency issue, right? So remember, we have this concurrency issue, and so maybe, for example, there's like a shop in the game, and the shop is maybe like the public state. Everybody has access to this public shop, and anybody can buy from this public shop. What if I try and use my gold to buy from the shop, but another player tries to buy from the shop at the same time, right? So we still have this concurrency issue. I have some proof that I have enough gold to buy an item, and this other person also has a proof that they have enough gold to buy an item, but who should get it? So the way Midnight solves this is with a system they call Oracle transcript, which will work very similar to reducers. And in fact, if you're familiar with the concept of UTXO based blockchains like Bitcoin and Cardano and many others, unlike Ethereum, a lot of these concepts will probably seem like rewordings or reinventions or a slight tweak on a lot of the ideas that UTXO blockchains have been talking about for many years. So, what are Oracle transcripts? Oracle transcripts is basically whenever you have a proof, a transaction that does something, the proof, because these are variable updates, specifies what it reads from, what it writes to, and then any condition. Right? Remember we said conditions, for example, it could be like, is the price still within a range? Is it within my slippage? Right? So any transaction you make has these things you're reading from, things you're writing to, and condition. And note that things you're reading and writing to could be in reference to the private state, or it could be in reference to the public state. So there's different kinds of Oracle transcripts. There could be like public transcripts based off reads and writes of the public state. We also have private transcripts or reads and writes based off the private state. Okay. So when you're making transactions in Midnight, you don't necessarily need to share them with everybody else, right? So for example, if you're playing a game, maybe I moved areas. I went to a different city. Maybe I captured some monsters. And then maybe I defeated an NPC and got some gold. And then I want to buy an item, which is what we talked about, in the shop. So to have this proof that you bought an item, you don't necessarily want to share all the actions you did. You don't want people to know you moved to a new area. You don't want people to know you captured a monster. You don't want people to know you defeated some NPC. You just want a proof that you can buy an item, right? So all this is all private state. This is why this private state is so important. It allows us to represent multiple transactions, multiple things you're doing on the blockchain as this private information that's never shared with anybody. And the only time you ever need to share something publicly and actually record it inside the blockchain is whenever you're actually doing something that modifies public variables that are shared. And whenever you modify public variables, you're not sharing your entire data. You're just sharing a proof that you can do this action. So this gives you massive compression. And so it allows you to build these massive games, massive real-world asset experiences, massive DeFi experiences in a way that scales really well, because the amount of information you're actually storing on chain is just these small proofs that you can do something. And you often never have to reveal a lot of the private state that led you to get there. Of course, you might want to reveal stuff later, like maybe you later on want to reveal some statement about the NPC you beat. Maybe later on you'll want to reveal some information about the monster you captured. Maybe later on you might want to reveal something about the area you're in. So there's cases where you want to reveal stuff, but it gives you the ability to decide when you want to reveal stuff. And Midnight, they call this leakage. So you're leaking private information. And the key thing about Midnight is you choose when to leak information and you choose what to leak. And by default, you're revealing the least amount of information possible. And so this gives you a really powerful way to build blockchains. And the fact that you have some information about reads and writes in this kind of transcript, you don't share this transcript. Maybe to kind of take a step back, um, this kind of stuff over here, this is basically a transcript, right? We have a bunch of actions we're doing to accomplish some goal, and these transcripts implicitly, read state and write state has some addition. But note the transcript does not really end there. Like maybe after buying an item, I want to use the item, right? And we want to make sure that if the user was not able to buy the item, if it got sold in the shop to the other player, that this fails, and nobody fails everything after this. So we need to have this concept of transcript. What is a series of actions a person does? And we need to somehow process these in order, and rather verify these in order, up until we get to a statement that no longer holds. You want to do this without revealing the statement themselves, right? So you want to, when we say we want to like prove that the user can buy an item, implicitly we're verifying they move to the area and they capture the monster and they feed him without revealing what they did, right? This is all private state. We're not revealing what they actually did. We're just verifying that there's some path. So this Oracle transcript allows us to hide what we actually did, but have a way of verifying that it's a valid path to an end of an action. And because these transcripts, every step from move area to capture monster, specifies the reason right it does, it allows us to detect if a conflict occurred implicitly. So instead of revealing, I defeat an NPC, you can say stuff like, I did something. And that something is valid as long as nobody else changes a specific part of the state. And be like, okay, like, yeah, there's nothing in the blockchain that contradicts the fact that you could battle an NPC, that's fine. There's nothing that contradicts the fact you could have captured a monster, that's fine. There's nothing that contradicts the fact you could move to an area, that's fine. And so you're just encoding the minimal amounts of leakage, the minimum amount of stuff required to verify there's some valid path you took. But when you get to an item, it's possible that some condition is not met. And so, from a public blockchain perspective, it's possible to say, like, okay, this public state tried to make some action that is no longer possible, right? Because we know that somebody else bought the item. And so, when we're processing this information, we can say, okay, these ones up to here were fine, but whatever action you were doing here, I don't know what it was, but you're trying to use some state that we know is no longer valid. So the Oracle transcript, a very clever way for us to encode this large set of actions we're doing on private state and public state, and somehow fail these whenever there's a conflict using the minimal amount of information required. And so the way these transcripts are implemented internally is kind of like a linked list, which is every action you do is an action within this linked list, right? And other people might have their own linked list of actions. So this is, like player 1, this is player 2. So everybody has their own private state, building their own list of actions. And then we have kind of like the public state. And whenever you're submitting a proof, you are essentially compressing this linked list. You're reducing this linked list to a single proof to go from one state to the other. right? So in Mina, we have this concept of reducers, where people submitted to a smart contract which queued up reducers, and then somebody else would come in later and apply the reducer. In Midnight, we kind of have a similar concept, but you are building the action queue locally with your modifications to your private state, or that's the wrong one, to modifications to your private state, and then your reduction of your private state is used to update the public state, which implicitly checks that all the steps are still valid given the current public state. So hopefully this gives you some insight on this. And by the way, if you want to read more, you can read the China paper. China is the name of the system used by Midnight that basically describes this whole Oracle transcript system. But hopefully that gives you some insight into how Mina and Midnight work, how they're both really interesting concepts and both enable very different things, but do it in a very different way that gives you a lot of power. Like, with the Midnight model, you can see dealing with state is much, much easier. What if you're doing computation that's not state, right? You're just doing something that is like a hash, and you want to hash a function or hash some data. You have to do this 1,000 times. There's really no state involved. You're just doing something that's stateless and doing 1,000 times. And you want to prove that you did this 1,000 times. When you have this kind of stateless thing, of course it is doable in Midnight, right? But it's much easier to think about this kind of thing in Mina, where you say, okay, it's just a function. I'm doing a function 1,000 times, and here's the proof of compressing a function. So there's cases like this where Mina actually ends up having a bit of like a clear model for how to implement stuff and combine stuff together. And so depending on what kind of dApp you're building and uh, how you as a programmer prefer to develop applications, there's some cases where maybe Mina is an easier model for you, and there's some cases where maybe Midnight's an easier model for you. And so they both have really clever ideas, really clever solutions to problem. And of course, because these are both products in development, they're always getting updates. And so, we talked about how Mina has some issues with state, and so they're building this system called Project Untitled, which is meant to have better state management, and I'll probably cover that in a separate video. Similarly, Midnight is, has this really awesome way for dealing with variables and conflicts and dealing with large state for applications in a very efficient way. But they're not a good for this competition stuff. But they're doing in parallel research into stuff like folding schemes, which are other cryptographic instructions that can probably help them a lot with being able to better handle stuff like this Mina use case of modeling stuff as functions. And so, as always in tech, things keep evolving. People come up with really clever things for one problem, and then try and borrow from others, or come up with new ways to expand their protocol. And so, I'm super excited to see how Mina and Midnight evolve over the coming years. But we at our team are very interested in both of them. We've worked with both of them quite a bit, and I think both of them are contributing a lot to the greater landscape. And so I'm really excited to keep working with these projects, contribute to some of these roadmap items like project titles and folding schemes and so on, and see how we can borrow ideas from each other and work together to keep pushing the frontier of what we're able to do with user-facing applications in the blockchain space. So if you like this kind of video, definitely let me know. And we have a lot more stuff we'd like to share with you. And so it's great to know what people want to learn, and we're happy to help people learn that.